Chapter 1 Rate of Reaction Class Life Sciences. Part 1 Theoretical Study. At the end of this session, students should be able to define average and instantaneous rate of formation of a product and of disappearance of a reactant, deduce the relation between the rate and the stoichiometry of the reaction. Introduction. During a chemical reaction, reactants disappear and are transformed into products. According to the duration of the progress, chemical reactions are classified into fast and slow. Fast reaction is an instantaneous reaction such that we cannot detect its progress. Combustion of hydrogen, precipitation reactions, and explosive reactions are examples of fast reactions. Slow reaction is a reaction that its progress may be measured during interval of time which could be seconds, minutes, hours, or even years. The reaction between acids and some metals and the corrosion of some metals are examples of slow reactions. This video shows an example or examples of slow and fast reactions. Okay. This solution containing silver nitrate solutions, colorless, containing Ag plus ions, we add sodium chloride solution containing Cl minus. We observe at the moment of the addition of Cl minus, we observe formation of white precipitate. This reaction is fast reaction because it takes place in one moment. By slow motion, at the moment of the addition of Cl minus, we observe the white precipitate, which is AgCl. Then this reaction is fast reaction. Another example of fast reaction between acid and base. We have in this beaker hydrochloric acid containing bromothymol blue colored indicator that gives yellow color with acid. We add base. When we add base, we observe the change in color from yellow to blue in a moment. This reaction is fast reaction also. In slow motion, at the moment of the addition of base, sodium hydroxide, we observe the formation of blue color because base with bromothymol blue gives blue color. Then this reaction is fast. This example of a slow reaction between sodium sulfate in first beaker, solution colorless, and second beaker containing hydrochloric acid, colorless beaker. In this beaker, we write the NS, 2 letters, and we add the colorless solution of sodium sulfate. Then we add the hydrochloric acid solution. After we have reaction between S2O3 and HO plus that gives sulfur solid of color pale yellow. After few seconds, observation is nothing. We observe change in color. The NS letters disappears gradually till we cannot see them after 1 minute 10 seconds due to the formation of sulfur. This formation is slow, so that this reaction is slow. Now, what is chemical kinetics? Chemical kinetics is the study of the progress of a chemical reaction with time. Slow reactions are the studied reactions in chemical kinetics. We cannot detect the progress of fast reaction, then we cannot study the kinetic of fast reaction, only slow reaction. And which slow reactions? The slow reaction that takes place a few minutes to few hours, not those reactions that take place with a few seconds, nor that took place with a few years, only few minutes to few hours. Theoretical study. Study of the variation during a complete chemical reaction. During a complete chemical reaction, reactants disappear and products are formed. That means the number of moles for each reactant decreases while that of each product increases with time. Tell the complete consumption of the limiting reactant, the moment at which the reaction ends. When the limiting reactant disappears completely, this is the instant of the end of the reaction in case of complete reaction. Consider the general equation of chemical reaction. Reactants are transformed to product. At an instant T1, we have N1 number of mole of reactant N1 and number of mole of product N1. At instant T2, number of mole of reactant becomes N2 and number of mole of product becomes N2. Reactant disappears, then number of mole of reactant decreases time, therefore number of mole N2 is less than N1 in case of reactant. In case of product, we have formation of product, then number of mole increases, therefore N2 is bigger than N1. The variation is N2 minus N1 is negative in case of reactant because N2 less than N1, is positive in case of product because N2 is bigger than N1. Conclusion: the variation in number of moles during a chemical reaction is for reactants delta N reactant equal N2 minus N1 less than 0 because N2 minus less than N1 since reactants disappear, and for products delta N product equal N2 minus N1 bigger than 0 because N2 bigger than N1 since products are formed. Definition of the rate. The rate of formation of a product within the interval of time delta T, which is equal to T2 minus T1, where T2 bigger than T1, can be expressed as rate of formation product is variation in number of mole over variation in time. The rate of reaction always has positive value. Of formation of product or disappearance of reactant always has positive value. The rate of disappearance of reactant within the interval of time delta T, where T2 bigger than T1, can be expressed as rate of reactant equal minus delta N reactant over delta T, because delta N reactant is negative in case of reactant. And to have positive value for rate, then we multiply delta N by minus, then the rate minus delta N over delta T in case of reactants. Now, we have two types of rate, average rate and instantaneous rate. Once we want average rate. Average rate, we have two types of average rate, of formation of product and disappearance of reactant. Now, of formation of a product. The average rate of formation of product is equal to the variation in the quantity of this product. Quantity could be number of moles or molar concentration over the interval of time between the two instants T1 and T2. Then the expression becomes, for the study of the variation in the number of moles of the product as function of time, NP equal FT, The average rate of formation of product equal delta N product over delta T and 2 minus N1 over T2 minus T1. Average is represented by R with bar or dash. That means average rate. For the study of the variation in the molar concentration of the product as function of time, concentration product equal Ft, average rate of formation of product equal variation in concentration over variation in time, concentration at instant 2 minus concentration at instant 1 over T2 minus T1. Now of disappearance of reactant. The average rate of disappearance of a reactant is equal to the negative of the variation in the quantity of this reactant, number of mole or molar concentration, over the interval of time between the two instants T1 and T2. For the study of the variation in the number of moles of the reactant as function of time, N reactant equal Ft, average rate equal minus delta N reactant over delta T minus N2 minus N1 over T2 minus T1. For the study of the variation in the molar concentration, the relation becomes minus delta concentration over delta T equal minus concentration 2 minus concentration 1 over T2 minus T1. Now, instantaneous rate is the rate at an instant t of formation of product. The instantaneous rate of formation of product rate at an instant t is the limit of the average rate when the interval of time delta t tends to 0. That means the time between t1 and t2 is 0, same instant. Rate of formation product equal limit when delta t tends to 0 of delta n over delta t, or limit of delta concentration over delta t. For the study of the variation in the number of moles of the product as function of time, it is equal to the derivative of the function n product equal ft. Rate at instant t equal dn product over dt. For the study of the variation in the molar concentration of the product as function of time, the function is concentration product equal ft. The rate is the derivative of this function. Rate at instant t of product equal d concentration the product over dt. Now, of disappearance of a reactant, the same for the study of the variation in the number of moles of the reactant as function of time, it is equal to the negative of the derivative of the function n reactant equal ft minus dn reactant over dt. For the study of the variation in the molar concentration of the reactant as function of time, it is equal to the negative of the derivative of the function concentration reactant equal ft. Rate of reactant at instant t equal minus d concentration reactant over dt. The instantaneous rate, we will see how can we determine the rate at an instant t graphically from the graph in part 3 of this chapter. Now, units of the rate. For the study of the variation in the number of moles as function of time, nf, n equal function of time, the unit of the rate is unit of the number of mole over unit of time. According to the unit of time, we have different units of rate. If time is in second, then the unit becomes mole per second. If time is in minute, then the unit becomes mole per second minute. If time is in hours, then the unit becomes mole per hour. For the study of the variation in the molar concentration as function of time, concentration equal Ft, the unit of the rate is unit of concentration over unit of time. If T is in second, then mole per liter per second. If T in minute, then mole per liter per minute. If T in hour, then mole per liter per hour. (1.5) Rate of reaction and stoichiometry. Consider the following reaction. AA plus BB gives CC plus DD, where capital A, B, C, D are reactants and products, small a, B, C, D are stoichiometric coefficients. According to the stoichiometry of the reaction, we have number of mole of A reacted over A equal number of mole of B reacted over B equal number of mole of C formed over C equal number of mole of D formed over D. For the variation in number of moles, the relation becomes minus delta N reactant over A, the delta N A reacted over A equal minus delta N B reacted over B equal delta N C formed over C equal delta N D formed over D. The variation in product is positive, while the variation in reactant is negative. For the equality to remain equal, we should multiply the variation in reactant by minus to obtain a positive value to equal the positive value of the product. Remark, since delta N reactant less than 0, we multiply delta N reactant by minus to become a positive value. Divide by the interval of time delta t, the relation becomes minus delta N A reactant over A times delta t minus equal minus delta N product reactant B reacted over B delta t equal delta N C formed over C delta t equal delta N D formed over D delta t. We multiply by 1 over delta t. Since minus delta N reactant over delta t equal average rate of reactant and delta N product over delta t equal average rate of product, therefore the relation becomes minus delta N A reactant over delta t is the rate of disappearance of A, it remains A, then the relation becomes average rate of A over A, minus delta N B over delta t equal rate of B, it remains B, equal delta N C formed over delta t equal is rate of C, it remains small c, and delta N D over delta t is rate of formation of D, it remains D. This is the relation between rate of reactant and rate of product. Rate of reactant A over A equal rate of reactant B over B equal rate of product C over C equal rate of product D over D equal rate of the reaction. Then the rate of the reaction is the rate of reactant or product divided by its stoichiometry, its stoichiometric coefficient. The same for the instantaneous rate. A rate of A over A equal rate of B over B equal rate of C over C equal rate of D over D equal rate of reaction. For example, for the reaction N2 plus TH2 give 2NH3, the rate of N2 over 1, stoichiometry 1, equal rate of H2 over 3, equal rate NH3 over 2, equal rate of the reaction. Application 1. Consider the reaction of net equation 2NO plus O2 gives 2NO2 during an interval of time delta t equal 100 seconds. The variation in the number of moles of oxygen O2 is delta NO2 equal minus 5 mole. A. Calculate during the same interval of time the variation in number of moles of NO and NO2. B. Calculate the average rate of disappearance of O2, deduce that of NO. C. Deduce the average rate of the reaction. Solution of application 1. According to stoichiometry of the reaction, stoichiometric ratio, minus delta N NO over H stoichiometry 2 equal minus delta NO2 over H stoichiometry 1 equal delta N NO2 over H stoichiometry 2. We are given delta NO2 equal minus 5. We can reduce delta NO and delta N NO2. For delta NO, minus and minus cancelled, then delta NO equal 2 times delta NO2 over 1. 2 times minus 5 over 1 equal minus 10 mole. For NO2, delta NO2 over 2 equal delta NO2 over 1. Delta NO2 equal 2 times minus delta NO2 over 1. That means minus 2 delta NO2 over 1. Minus 2 times minus 5 over 1 equal plus 10. Variation for reactant is negative, variation for product is positive. Now, average rate of O2 equal minus delta NO2 over delta T equal minus delta NO2 equal minus 5, minus times minus equal plus 5 over 100 equal 510 power minus 2 mole per second. Now we should deduce from the rate of O2, we should deduce the rate of NO. Now according to the stoichiometry of the reaction, average rate of NO over 2 equal average rate of O2 over 1 equal average rate of NO2 over 2 equal average rate of the reaction. Average rate of NO equal 2 times average rate of O2 over 1 equal 2 times 5 10 minus 2 over 1 equal 0.1. 10 minus 2 equal 0.1 mole per second. See, average rate of the reaction, we take rate of O2 over 1 or rate NO2 NO over 2. Rate O2 over 1 equals 5 10 minus 2 over 1 equals 5 10 minus 2 mole per second. This is the end of part 1 theoretical study.